Good morning, friends. Today we can see the design of circular slab which is partially fixed at the edges. So before moving on to the problem, we can directly go to the equations of the same. So let us consider a circular slab having a radius capital R which is partially fixed at the edges and which is having a UDL of W per unit area. At a radius small r, from the center of the slab, the values of mr and m theta are as follows. Mr equal to W 2r square minus 3r square divided by 16. The value is positive. Similarly, m theta equal to W 2r square minus r square divided by 16. That too is a positive value. And at the center of the slab, so what is happening at the center? At the center, your small r will be equal to 0. So at the center of the slab, mr equal to m theta equal to plus 2wr square by 16. And at the support or at the edges of the slab, where small r equal to capital R, we have mr equal to minus wr square by 16 and m theta equal to plus wr square by 16. The maximum shear force at the support will be equal to W into capital R. And here we have to find the point of contraflexure. The point of contraflexure lies at a distance of small r equal to root 2 by 3 into capital R. Just refer the figure here. So here we have MR diagram, M theta diagram as well as shear force diagram, and in the MR diagram you will be getting the positive moment that is at the center as well as a negative moment at the supports. So positive MR as well as negative MR is there, and in M theta diagram you will be having support moment which is positive, that is WR square by 16, and also the span moment which is also positive, which is 2WR square by 16. Fine. So now we can move on to the problem. So question number 3, I will read out the question. A circular slab for a room of inside diameter 6 meter is partially restrained at edges. It carries a superimposed UDL of 4 kN per meter square, including that of finishes. Use M20 grade of concrete and Fe415 grade of steel. So as usual procedure only, then nothing more in that. So step 1, we have already done 2 problems earlier. So step 1, design constants. From that you will be getting mu limit equal to 2.76 bd square. And step 2, dimensioning of the slab. Same, L by D ratio equal to 45 meter. L effective 6.23. D provided approximately equal to 150 millimeters. And capital D equal to 180 millimeter. And now we have to find out the effective span. The effective span will be the lesser of clear span plus effective depth as well as the center to center distance. So effective span will be equal to 6.15 meter. Therefore effective radius will be equal to 6.15 divided by 2, that is equal to 3.075 meter. The same steps. Step number 3, load calculations. So after getting the load calculation, here why we are not going for this finishing loads, because in the question itself it is given as it carries a superimposed UDL of 4 kN per meter square, including that of finishes. Therefore no need of taking extra finish loads. So this 4 kN per meter square includes finish loads also. So this factor load is 12.75. and next is you have to find out the bending moment and the shear force. So bending moment and shear force as per the equations at the center of the slab as well as at the support we have to find out. At the center of the slab, mr equal to m theta equal to 2wr square by 16, that is equal to plus 15.1 kilonewton meter, and at the support or at the edges mr equal to minus wr square by 16, just remember that figure, and m theta equal to plus wr square by 16. So minus 7.5 kilonewton meter and plus 7.5 kilonewton meter. So these are the bending moments, and we have to find out the ASTs corresponding to these bending moments. And also we have to find out the point of contraflexure, that it occurs at 2.51 meter from the center. Just read the figure. From the center, I have marked 2.51. That is the point of contraflexion. And just mark all these values in the figures. And next is step number 4. Check for D required. Before that, we have to find out the maximum shear force, that is 39.2 kilonewton. And now we have check for D. So mu equal to Ru into B D square. D required equal to root of mu by Ru into B. That is equal to 73.96, which is less than 150, which we have already provided. So mu is less than mu limit. Hence we can go on for the slab as a singly reinforced slab or under reinforced slab. And now we have to find out the steel reinforcements for MR and M theta. So in order to do that, we have to find out D average, and we got the D average as 146 mm. And for MR and M theta at the center, we are getting an AST of 276 mm square, and for that AST we are providing a spacing of 180 mm, and we just found out the AST minimum, and we check that AST provided is less than AST minimum. AST minimum is less than AST provided for the bending moment. Therefore, provide 8 mm diameter at the rate of 180 mm center to center in the form of mesh at the center. And now it is step number 5. We have to find out the AST for negative MR, which is at the support. So for that, we have to calculate D equal to 150 mm. So 77.5 into 10 raised to 6 is the moment MR here. Negative sign just indicate only the bending moment at the support. No need to consider it for the calculations. So here AST minimum is getting AST minimum value is more than AST required. Therefore, we are taking AST minimum as the main AST, and we have just provided the spacing according to the AST minimum. Therefore, provide 8 at 300 mm center to center at the support. These are the top reinforcement. And now just find out the distance from the support to the point of contraflexion. So this distance, just refer the figure also. So this distance is 3.075 minus 2.51, that is equal to 565 mm. So up to this 565 mm, we have to provide rings at the support. So number of 8 mm diameter rings are required at the support equal to the distance divided by the spacing, 300 mm spacing, plus 1. Therefore, 3 rings you have to provide at the support for the top reinforcement. And therefore, again we have to calculate the AST for the positive M theta at the support. That is M theta diagram. Just remember, M theta diagram, there will be positive M theta which has to be given at the support. Positive M theta in the form of rings. So for that, AST equal to 7.56 into 7.5 into 10 raised to 6. AST getting is 140 mm square, which is very much less than AST minimum. So we are just choosing AST minimum as the main AST, that is 216 mm square, and we have to provide 8 mm diameter rings at 300 mm center to center as the positive reinforcement at the support. We have to provide the positive reinforcement at the support. And now we have to calculate the development length of the same. So the development length will be equal to 376. Equal to 376 mm. Assume 8 mm diameter for rings. So we have to calculate the number of rings which we need to provide at the bottom of the circular slab, that is for positive moment. So number of rings can be calculated by using can be calculated by 2 ways. Okay, the first way I am just telling you, see, A or B. So number of rings required equal to that development length divided by spacing of the main bar plus 1, that is equal to 3 rings. And now we have to provide these rings for a distance of 565 mm from the support. That is, up to the point of contra flexure, we have to provide this rings. Therefore, we are just taking the spacing required for this rings as this 565 divided by number of rings, that is equal to 188 mm center to center. And another way of finding out the ring is, spacing of the ring is, assume again 8 mm diameter rings, and now just consider area of cross section of a single ring, that is equal to pi by 4 into 8 square, that is equal to 50.265, and now number of rings required equal to 216 divided by 50.265. So where did this 216 come? So this 216 is the AST provided, 216. So AST divided by area of cross section of one ring will give you the number of rings, the 4 number of rings. Therefore the spacing of rings will be equal to 565 divided by 4, that is equal to 140 mm center to center. In both ways you can calculate a number of rings. Okay. At any case you just give the number of rings at least equal to 3 numbers. That you just keep in mind. Number of rings should be kept as a minimum of 3 numbers at the bottom plan. Okay, and I am just adopting A. Therefore providing 3 number of rings of 8 mm diameter at 188 mm center to center. Fine. So 188 mm center to center. I am just providing 3 number of rings. And next is, as usual procedure, step number 6, that is check for shear. So VU 39.2 kilonewton, tau V equal to VU divided by BD, and PT, just take the maximum area provided, that is 8 pi by 8 square into 1000 divided by 180, so that we will be getting the percentage for the maximum area of cross section. So PT equal to 0.18 percentage, tau C equal to 0.29. So tau V is less than tau C is less than tau C max, therefore it is safe. And the last and final step is step number 7, check for the development length at the support. So LD as usual less than or equal to 1.3 M1 by V plus L0. Here also M1 you should take M1 equal to 14.5 kilonewton meter. Therefore 47 times diameter equal to should be less than or equal to this 1.3 into 14.5 into 10 raised to 6 divided by 39.2 into 10 raised to 3 plus L0, 150 mm. So diameter should be less than 13 mm diameter. Therefore we have already provided it as 8 mm dia, therefore it is safe. And now we can move on to the detailing part. Just refer the figure. So in the sectional elevation we can see, so see here in the sectional elevation, so both the top and bottom reinforcements are shown in the figure. See? Yes. So this bottom reinforcement shows 8 at 180 mm center to center bars, which are provided in the form of a mesh, right? That is the reinforcement at the center. Similarly, what about the ring bars which is shown towards the support? That is for the positive moment which is coming at m theta moment, which is the positive moment towards the edge of the slab. So for that edge we have found out 3 number of rings, that is at 188 mm center to center, 8 mm diameter, 188 mm center to center rings which are placed at a distance of 2.54 from the support. So these are the rings which we have to show at the bottom plan. And now we can move on to the top reinforcement. So in the top reinforcement we already found out the negative reinforcements, that is 8 at 300 mm reinforcement radially as well as circumferentially. In both directions we have to show and we have to mark in the figure. So just for the top plan as well as the bottom plan. 8 at 180 mm bars and the rings 8 at 188 mm center to center spacing, and the top plan 8 at 300 mm in both ways. So this is the video showing problem number 3. Just go through it and please contact me if you are having any doubts and clarify it as early as possible. And one more question I am planning to give you, the same type of problem. I need everyone to do it separately, and I will dictate the problem. So please note down that problem also. A circular slab is 5 meter effective diameter, which is partially fixed at the edges. It is loaded with a UDL of 5 kN per meter square. FCK is 20 Newton per mm square and Fy is 415 Newton per mm square. Please try to do this problem and kindly send me the draft of the same. You can just take a pic of the same and you can send me either through WhatsApp or you can just paste it in Google Classroom, so that I can have a look on that, so that I will get an idea that whether you people understood anything in this previous classes and all. So please try to do this problem as an assignment and just paste it in Google Classroom, or you can send me as an image through WhatsApp. Okay, thank you.